Every time you click a mouse, you are triggering a physical stampede of electrons. At the heart of your machine sits a slice of silicon no bigger than a fingernail, containing over 50 billion individual switches. This is the CPU, the most complex machine ever built by man. It operates on a cycle so fast that if 1 second of CPU time were equal to 1 human heartbeat, a single minute of computer operation would last for over 30 years. But how does it turn raw electricity into a high-definition video or a complex calculation? It begins with the simplest concept in the universe: yes or no. To understand the CPU, we have to zoom past the motherboard, past the silver casing, and into the microscopic architecture of the silicon die itself. Here, the landscape looks less like a machine and more like a sprawling, multi-layered metropolis of light. Every single thing you see on your screen, from the color of a pixel to the physics of a 3D explosion, is built out of just 2 ingredients: 0 and 1. In the physical world, these aren't just numbers. They are states of electricity. 1 is a flow of current. 0 is the absence of it. But how do you control billions of flows of electricity at the same time? You use a transistor. Think of a transistor as a gatekeeper. It is a solid-state switch with no moving parts. At this scale, we are working with layers of silicon so thin they are measured in nanometers, roughly the width of a single strand of human DNA. Inside the transistor, there is a channel that electrons want to flow through, but blocking that channel is a gate. When the CPU wants a 0, it keeps the gate closed. The electrons pile up, unable to pass. The circuit is off. But when the CPU applies a tiny burst of voltage to that gate, it creates an electric field that literally pulls the electrons through. The gate opens. The current flows. The 0 becomes a 1. This single act, opening and closing a gate, is the heartbeat of the digital age. But a single switch can't think. To create intelligence, the CPU begins to wire these switches together into logic gates. This is where the magic happens. By arranging transistors in specific patterns, the CPU can make decisions. An AND gate only lets electricity through if 2 switches are flipped at the same time. An OR gate lets it through if either switch is flipped. It sounds simple, but when you stack millions of these gates on top of each other, you create a physical language. But how does a collection of yes-no gates actually solve a math problem? How do you turn a flick of a switch into the number 5 or 10 or 1,000,000? It's all about position. In our base 10 world, we count from 0 to 9 before we move to the next place. In the CPU's binary world, you only have 0 and 1. To count higher, the CPU simply adds more places, or bits. Imagine a row of 4 light bulbs. If only the first one is on, that's a 1. If only the second one is on, that's a 2. If both are on, you add them together to get 3. By the time you have 64 of these switches in a row, you can represent a number so large it exceeds the number of grains of sand on Earth. To perform addition, the CPU uses a specific arrangement of logic gates called an adder. When 2 pulses of electricity, representing 2 numbers, enter this circuit, the gates interact. If 2 1s hit the gate, the logic forces the electricity to carry over to the next column, exactly like you did in primary school math, but at the speed of light. Whether it's calculating the trajectory of a rocket or the shade of a pixel in a video game, the CPU is just doing billions of these tiny additions every microsecond. But there is a problem. These switches are now so small that we are hitting the edge of known physics. The walls between these gates are now only a few atoms thick. If we go any smaller, the electrons don't wait for the gate to open. They simply teleport through the wall. This is quantum tunneling, the ghost in the machine that threatens to melt your processor if we push it too far. But how does a CPU know what to do next? It doesn't know anything. It follows a relentless internal rhythm called the clock cycle. Imagine a conductor leading an orchestra of 50 billion musicians. Every time the clock ticks, the entire CPU performs one step of a calculation. When you see a processor rated at 5 gigahertz, it means that internal clock is pulsing 5 billion times every single second. Inside this heartbeat, the CPU lives in a 3-step loop: fetch, decode, and execute. First, the fetch. The CPU reaches out to the RAM, your computer's short-term memory, and pulls in a line of binary code. At this stage, it's just a raw string of ones and zeros. It looks like noise, but to the CPU, it is a specific order. Second, the decode. This instruction enters the control unit. This is the translator of the chip. It breaks the binary string apart and determines which logic gates need to open and which need to close. It's like a massive railway switchboard, instantly rerouting thousands of trains at once. Third, the execute. The control unit sends a pulse of electricity to the ALU, the arithmetic logic unit. This is the CPU's calculator. Here, the transistors flip, the math is performed, and the result is sent back out to be stored. But as we demand more speed, the clock has to tick faster. And here is where we hit the power wall. Every time a transistor flips from 0 to 1, it generates a tiny, microscopic burst of heat. 5 billion flips per second across 50 billion transistors creates a literal inferno. If you took the cooling fan off a modern high-performance CPU, it would generate enough concentrated heat to burn through the motherboard in seconds. We are no longer just fighting physics, we are fighting thermodynamics. To solve this, engineers didn't just make the clock faster, they gave the CPU more brains. They created multi-core processing. Instead of one giant genius working at a deadly speed, we have 8, 16, or 64 smaller workers sharing the load. But even with multiple cores, there is a bottleneck. The CPU is so fast that it often has to wait for the RAM to send data. To a CPU, waiting for RAM is like a human waiting 1,000 years for a letter to arrive in the mail. To fix this, we built the cache, a layer of memory sitting directly on the silicon die, just micrometers away from the cores. It is the most expensive and fastest memory on Earth, and it is the only thing keeping the Metropolis of Light from standing still. But even with multiple cores and lightning-fast cache, the CPU is still a general. It is a single genius designed to handle one complex task at a time. This is fine for a word processor, but modern life demands something different. When you play a video game or train an AI, your computer isn't doing one complex math problem. It's doing millions of tiny, simple ones simultaneously. This is where the GPU takes over. If a CPU is a single mathematician, a GPU is a stadium full of 10,000 students, all solving basic addition at the exact same time. This is parallelism. It is the reason we can simulate reality in real time, and it is the foundation of the AI revolution. But that's another topic. For now, you know how a CPU works. Like and subscribe.